Thank you very much for the kind introduction. I would also like to thank the organizer for the kind invitation for me to be able to share with you some of the work that we have been doing at our university, and also to provide a general introduction to the different emerging technologies that can help maintain a healthy environment. One of the motivation that I have over the years is that it's because since 1940, there's a recorded of more than 300 new infectious diseases. Okay, so that means to say every decade we are seeing close to 50 new diseases coming out, and respiratory illnesses have the heaviest toll on human and the economy. Indeed, currently with COVID-19, there's more than 1.3 million people already lost their lives. And at the same time, it's estimated that the global economy suffered about 8 to 16 trillion dollars in lost activity. So that means to say it's very important, okay, to have a technology that can mitigate the spread of these respiratory diseases. The other major concern that we have is the worldwide prevalence of the AMR, or antimicrobial resistant organisms, that are resistant to many of these existing treatments. So as I already mentioned, the situation is like this large-scale infectious event is occurring very regularly, and in most cases become much more closer to one another. And the growing microbial resistance and tolerance is very important concern. And it is expected by 2041 that this is going to be one of the major cause of death, okay, globally. Now, respiratory pathogens are difficult, especially viruses. For example, a lot of envelope viruses, the one that we are most familiar with are influenza viruses, and more recently, the coronavirus can cause respiratory illnesses. But there are also a lot of non-envelope viruses that are very difficult to disinfect and inactivate, such as rhinovirus, enterovirus, adenovirus, and the emerging vocavirus that can also cause respiratory illness. Okay. There's always, I think, usually a thinking that envelope viruses are very easy to inactivate or kill. But in fact, many of these viruses, including influenza and coronaviruses, can survive in the environment for a prolonged period of time and remain infective, indicate that this is basically a important misunderstanding. Okay. The route for human-to-human transmission had already been established by Leo. Okay, it's usually through droplets, aerosols, and fomites. Okay, and that is very important. And in fact, for SARS-CoV-2, especially in many places, aerosol is confirmed to be one of the major transmission routes. We have been working in this particular area since 2003 when SARS happens in Hong Kong. Okay, at that particular time we developed the first generation of what we call catalytic air sanitizer, and this had been clinically tested in one of the Wan Chai clinic during SARS, and also in one of the heavily handicapped home in Hong Kong. Later on in around 2004, end of 2003, we were approached by an industrial partner or a sponsor, okay, who had a very close relationship with the Beijing government. So at that time, Beijing is trying to bid for the 2008 Olympics, and they have a deep concern that SARS is going to become a recurring event. It's going to be a seasonal problem. So at that time, the small think tank group, which consists of medical doctor, epidemiologists, and others, come up with a list of what they call wish lists for a technology that they would like to see implemented if SARS remain current and they need to host the Olympic. And one of these is lead to what we now term as the smart antimicrobial system. So what they wanted is something that is very safe, easy to implement, very discreet in that there's no that is transparent. You cannot see it, you cannot feel it, okay, you cannot taste it, and it can last for a long period of time. So it had to last for at least 1 month because Olympic lasts for about 25 days. So that led to the first generation of smart antimicrobials, um, which later on we translated into antiviral air particulate filters, which play a role in the early outbreak of the COVID-19 in Wuhan. In fact, it had been used in the Hushinshan Hospital as a first line of defense against like aerosol and droplets, because it's the only material that have been rated for MERS-CoV. Okay, and and later on we will also discuss about like multi-level antimicrobial polymers for surface protection. So the antiviral filters is actually based on encapsulated chlorine dioxide. Okay, chlorine dioxide is a very potent like disinfectant. Okay, it can kill microorganisms very rapidly. The other important issue is that chlorine dioxide, unlike other type of disinfectant, doesn't need the water breach to bring out the disinfectant. Okay, so that means to say it's in a gaseous form. It can be released, okay, to do disinfection. So that means to say it's less sensitive to fouling of the filter surfaces, because a lot of the filters that is currently that are antimicrobial, they are contact healing. However, the filter also accumulate other dust particles and other type of like the foulants, and therefore the microorganism may not be in direct contact with the filter material. Therefore, the efficacy will be much less. But with chlorine dioxide, which is released as a gaseous phase, it can actually tolerate heavy fouling of the surface. So it allows it to be very effective. So this has been extensively tested not only by our laboratory, but also by a certification lab to be very effective against like different type of viral particles, including influenza, enterovirus, syncytial virus, as well as the MERS-CoV. So this is a filter system that we actually also field tested in one of the elderly home in Hong Kong. In addition to the field test, we also do like engineering modeling. Okay, for example, in this particular case, we look at the way that it can clear, okay, the bacteria, okay, from the room. Okay, this is modeling one of the residence room in the elderly home. So in this case, the filter is placed on the air conditioning, which have sufficiently high airflow. So what we can see that it can very quickly clear up a microorganism from the room. Okay. So this is a modeling figure, which is backed up by experimental measurements. So how does it work? Chlorine dioxide is actually it's an oxidizing like disinfectant. So one way that it can disrupt the viral particle is by oxidizing and damaging the capsid. Okay, so we can illustrate that for both H1N1 and H3N2. Okay, viral particles. The other thing is like it's actually like interfere and disassemble the spike itself. So we can monitor that the H and N surface protein in this like influenza viruses are basically disappear or damaged, okay, after exposure to this material in less than 1 minute. And then it's also this damage and destroy the DNA and RNA, because like there's a lot of study, like for example, influenza viruses and even the SARS-CoV-2, the RNA fragment can still be infected. Okay, so this shows that we are actually targeting different biological compartment and along different inactivation pathway in order to inactivate the microorganism. By doing this, we actually reduce the likelihood that tolerance and resistance can emerge. Okay, because you are actually targeting inactivation through different like routes. It also presents like contact healing, release killing, as well as anti-adhesion property in order to reduce the colonization on the surface of the filter materials. Is it safe? Okay, we did a lot of study because one of the concern that we have is like whether inhalation safety, because chlorine dioxide can be released in the gaseous phase. So we did a lot of extensive study, including like the in vivo test using like cell line, lung cell line, wherein we demonstrated that it is quite safe. And we also did animal model study wherein we look at the lung function on the exposure installation of this material, and also follow the leukocyte, lymphocyte, and neutrophil to see whether there's any inflammatory effect due to the exposure to these materials. Then after we have make sure that it is both effective as well as safe, then we did almost 12 months, clinical field study in a palliative care unit of a Haven of Hope Hospital. So we recruited 7 sites within the palliative care unit, and we basically demonstrated during the 12-month period the general reduction in the amount of airborne bacteria during this time, and we can show that it is effective in terms of maintaining a good air quality within the residence as well as in the nurses station and in communal area. Now there are many technology nowadays that you would see in the field that talk about effectiveness against fomite. One important emerging technology are PCO, photocatalytic oxidation, and the other one is the chelated compounds. Now, PCO work because there are many semiconductor materials. Okay, when you expose them to light, okay, it's able to basically separate electron, okay, from the atom and generate a hole. The electron then react with the water vapor within the air to generate hydroxyl radicals. So this is what we call reactive oxygen species. And then the whole can react with oxygen to form superoxides. Now, the major workhorse is the hydroxyl radical, okay? So this is the one that basically react with the with molecule or biomolecule in order to oxidize them and create damage, okay? Now, PCO are very good, okay, for very simple molecules. So they are very effective in removing organic pollutants like formaldehyde or toluene or others, or smell, okay, from the room. However, in order for them to kill microorganisms, it's not sufficient. Especially bacteria can self-repair, okay? So what happens is usually most of the PCO that are used to treat or kill microorganisms, they contain heavy metals, okay? So the usual heavy metal that will be used are platinum, silver, or copper, okay? And in fact, even the chelated compound uses platinum, chelated platinum. However, I think everybody knew that heavy metals, especially nanoparticles, do have some hidden risks, okay? Especially there are a lot of reports how these heavy metals can have neurotoxic effect. Some of them are contributor for Alzheimer's diseases. So these are more chronic, okay, issues that are related to the heavy metal system. So photocatalysts by itself, okay, like for example, titania, are not very effective. In order to boost up the effectiveness, you need to add all this heavy metal in the system. So that is one of the concern on the use of the photocatalyst. In fact, I spent a decade working on photocatalyst material, okay? And we do understand how to make them effective against different materials. Now, the other major line of technology against fomite, okay, that could give a long-term protection on surfaces are actually based on quacks, okay, quaternary ammonium compounds. So there's a lot of products out there that are actually quat-based, okay. However, quacks on and off have also other issues related to their safety, okay, and toxic effect and impact on the environment, okay, long-term impact on the environment. So this drives us to look at the possibility of developing something that is effective but simultaneously still safe, okay? So this is where we come up with the multi-level antimicrobial polymers. We decided to use polymers because a lot of time polymers are safer because they are bulky molecules. They're less likely to go through the cell. So that's number one. Number two, we selected like the polymers that are already rated by FDA for use in food packaging. Okay, so one of the material here are actually used in food packaging material. The other one is actually used as a food additive. Okay, materials. Now, the way that we achieve, okay, the antimicrobial property is how we assemble it, okay? So the moiety and the presentation of the moiety is one of the way that we increase the effectiveness of this material as an antimicrobial. So we can achieve anti-adhesion and anti-biofouling. We can also achieve like contact healing. So the material, we can also design how big are these like the micelles. So we usually design it to be around 600 nanometer because that can be easily cleared, okay, by the upper respiratory system. So it doesn't go in depth into the lung. So by design, we already can manipulate it to make sure that it is safe. Okay, so there are a number of things that we have done. The first study that we have done is to look at both like the drug-sensitive bacteria as well as drug-resistant bacteria. So we look at S. aureus, MRSA, their effectiveness, and all of this is 1 minute contact. Okay, so all the data that we are presenting is 1 minute contact because we wanted to later on use it for certain application in your neighbor, Kowloon Hospital. So we tried for S. aureus, E. faecalis, Pseudomonas, E. coli. So we did it for MRSA, BRE, MRPA, MDRA. So we also tried to use it for different types of spore, especially for Candida albicans as well as Penicillium chrysogenum. So they are quite good within like 1 minute contact. In Niger is much more difficult. Okay, so that is one thing that we have done. The other thing that we were curious at that time, they are very good against bacteria and spore. Viruses should be easy. So we did an initial study before the pandemic. We tested it for measles, mumps, and rubella because at that time there was a outbreak of measles. Okay, so we did testing in the secondary lab, and then we tested for feline calicivirus, which is again model for norovirus. Okay, and as well as Penicillium and Aspergillus spore. In their study, Aspergillus spore worked well. Okay. So in our own lab, we tested for MS2 phages, which is again a model for norovirus. And later on, we were able to have it tested for human coronavirus and more recently for SARS-CoV-2 virus, okay, material. So it can show that this material is quite effective against coronavirus also. Now, before we can go to the hospital to do our clinical field test, we have to, again, make sure that it is safe. So we, in this case, because this is going to be coated on items, we actually look at the in vivo test, okay, in order to model like the inhalation safety, ingestion, as well as contact safety. So we benchmark it against bleach, and then we look at the viability of the cell after exposure. So we've shown that this material is far more safer than 1:49 bleach or 1:99 bleach in terms of cytotoxicity. Then we also did the volunteer test in terms of contact because like we wanted to know whether direct contact onto skin, okay, will it have any sensation? So that is one issue. We also did animal study on rabbit, okay, in terms of like safety. So after passing all of this, then we also interested in the durability. So durability, we benchmark the material as a coating against paint. So paint has a certain like the adhesion strength. So how much force that you need in order to peel off the paint. And we see that it is almost comparable to that of the paint material in terms of like the robustness. Then we also did a wiping study, okay, using dry cloth as well as wet cloth with water, bleach, Dettol, detergent, alcohol, as well as CGW is Campbell Green Water because they said they use it a lot, okay, for doing this. So we did about 500 times like the simulated wiping, and then we do the test against bactericidal activity against S. aureus. Then we carried out the study in the Kowloon Hospital, because at that time they do have an issue regarding like the privacy partition curtain, that they find there's a lot of MRSA on those curtain materials. And they are concerned that this is actually a source of the hospital-acquired infection. So, and they also at that time tested several type of commercial like the antibacterial curtain material, but the performance is not as expected. So they invited us to carry out a study. Okay. So this is the result of the 7 months study with close to 2,000 samples, with 900 about 900 control and 900 treatments. We've shown that we can actually maintain over the 3 weeks period between changes in the curtain materials, that we can maintain about 96% less, okay, bacteria on the treated curtain, and about 98% less, okay, MRSA present in the treated curtain material. And then we were able to do extrapolation. We showed that to reduce the performance down to 70%, it will take about 20 weeks of direct use of these materials. The other thing that we have that we are doing is formulating this directly as a fabric softener that can be used directly in the laundry. Okay, so in this case, we did a clinical study in the Haven of Hope Hospital in the elderly care home for 6 months. And then initial study was shown is that the bedding material is heavily colonized by a lot of like drug-resistant microorganisms, including MRSA, BRE, MDRA, MRPA. Okay, so there are also Acinetobacter and Klebsiella found in the bedding material. So we decided to carry out the study there. So we collected about 258 samples over the 6 months period. So they changed the bedding once a week. Okay. So this is the study. We can maintain about 90% reduction in the MRSA from the between control arm and the treatment arm during the study. Okay, so that means to say it can be very effective in reducing bacterial load. Currently, we are carrying out a study wherein we are continuing this in collaboration with Haven of Hope, as well as Tonghua Group of Hospital and UMA. And we are also doing deliberate contamination using MS2 bacteriophage and 5,6 bacteriophage in order to simulate like the viral viability on the treated bedding materials. The material is highly versatile. So it can also be formulated into longer lasting system. Like for example, we can formulate it into epoxy coating for use in water pipe board, okay? Because it's very safe, it can actually pass the BS 6920, okay, which is actually for the intended for drinking water applications. It can also be used in very harsh environment, like for example, in the sewer and the storm water. In this case, we use it as a way to protect the concrete surfaces against like the microbial corrosion. Okay, because in the sewer there's a lot of microorganisms that can corrode the concrete material. So these are also showing that this type of technology is much broader based. So it can actually reduce the corrosion. Okay, as you can see, the concrete pieces can be heavily corroded. Okay, without the protection of these materials. The other thing is like this material can also be easily formed into like the filter system because they are polymers, so we can actually electrospin it. So the electrospinning is very fast because you don't need a very heavy layer in order to achieve capture of the particles, because this material itself have a charge on the surface, so it can capture viral and bacterial particle rapidly. So we can get 98% filtration with better breathability than N95. and we can achieve like the high bacteria inactivation and that of virus inactivation. And you can formulate it to release fragrance and other things, okay, in the system. Now, for water, we are also interested in looking at the water problem. Okay, we have been working in the water problem related to microorganisms, bacteria, okay, in the water. Because like there are many drainage outlet that goes into the Victoria Harbor, but simultaneously in the Victoria Harbor, we do a lot of like the sporting activity, recreational activities. And in this case, what we do is like we suppress the odor by targeting microorganisms that kill, that generate the odorous materials. So this is now being used in more than 300 locations in Hong Kong with malodor problem. And then before, okay, the pandemic, whenever they have the New World Harbor race or the Carnival race, they do deployment in order to suppress the odor. But it's also have an impact on the E. coli like content, because during one of the diversion, because the main water treatment plant in Hong Kong is under maintenance, they actually have to do a diversion, and they release the sewage directly into the Victoria Harbor at that time. So we did a massive deployment during that time, and then we can demonstrate that we can suppress the total bacteria in the harbor water during that period of time. Now, in a project that we are doing right now, okay, we are interested like about flush water, okay, because people know that that COVID-19 can be transmitted from different aerosolized droplet, including that of the urine, okay. So in this case, what we had shown here in this particular system is that we can actually formulate it into small beads. And when you deploy it into water, it will change color. It will then settle down at the bottom, okay? And then release the disinfectant. In this case, it's chlorine dioxide. Once it's finished releasing, it will float out so that you can flush it out from the system. Okay, so this is one of the example of what we call smart material. So we specially designed it for the specific application. Are they effective or not? So they are very effective. So we've shown that it can actually maintain close to 3-log reduction against E. coli. For MS2 phage, toward the end of the deployment on the 24th day, we still have about 95% reduction of the MS2 phage, okay, under deliberate contamination of the treated water. Another technology that we actually tested out is the high-intensity narrow wavelength technology. This one uses a combination of lighting, okay, material to rapidly disinfect surfaces, okay. This has come out from the project that we worked together with QEH, okay. And then what we did is like we also did a clinical trial in the elderly home, because we know that the bedding material is heavily contaminated, and their routine is that they only do washing once a week. So how can they maintain cleanliness of this material? So using this type of lighting, we can actually reduce the MRSA by more than 99%, okay, during treatment. So we can have it as a portable type, okay. One charge can last you about 2 weeks, okay, so because it's used very little energy. Or we can make it into an autonomous system, just like shown here in the video. So this is for the bedding, okay, so it's actually designed to be able to move in soft material or bedding material. And then while it's moving, it will actually do the disinfection of the surfaces. The same for hard surfaces. It can also do rapid disinfection. In fact, we are working with Lee Hazen Foundation, also with the high school students, okay, to prepare around 200 of this unit for distribution to different like elderly home in Hong Kong. So we already make all the kit. So we are waiting for the high school student to assemble it for this distribution. The last thing that we would like to present is related to our work on microneedles. Because now with the vaccine looming in the horizon, there's always one of the bottleneck that is not really being addressed. Okay, is that how do you distribute? Okay, the vaccine material, especially one of the bottleneck is the syringe. Okay, the needles, as well as the people implementing it, who's going to do it. So this technology, the microneedle, allow you to self-administer because it's simple, and then all the presentation of the vaccine will be just underneath the subcutaneous layer, wherein you have the highest number of dendritic cell. In fact, we did a study 2 years ago, wherein we do vaccination of using influenza vaccine on mice, okay? And then we measure the antibodies using ELISA. So we can see that the using microneedle for the same dosage, okay, you can get 9 times more response to ELISA because the presentation is right underneath the skin layer, okay? And I think it takes a lot of practice from the nurse to be able to do this type of like correct like the presentation of the vaccine material. The other important issue is it's painless, so you can ensure that there's more compliance. Okay, if that is going to be distributed, it doesn't generate a lot of medical waste, so there's no sharp waste that is generated. It's relatively easy to use, it's effective, and also at the same time, it's also inexpensive. Okay. So these microneedle are biomimetics. So they are made out of glass-like material. So they are very similar to nettle. Okay, nettle. You brush against it, then you have this problem because these are glass-like like the needles. Okay, on this material. So I will end my talk here. Okay, with an acknowledgement to all our sponsor as well as the student that really did all the work. Okay, thank you very much.